The first look behind a black hole has now been achieved by researchers, and in this video, you will learn all about it. So stay tuned. Of course, don't forget to subscribe to my channel to not miss any more space videos. Each of you who subscribes helps me a lot to continue my work here. Thank you very much, everyone, and welcome. Black holes definitely belong to the most fascinating objects in the cosmos for me. And not just because they play an important role in my favorite science fiction film, Interstellar. Their gravity is so strong in a certain area that even light cannot escape. The boundary beyond which gravity becomes light-consuming is called the event horizon. Most black holes are very, very heavy. But it is a widespread prejudice that a black hole necessarily has to be incomprehensibly heavy. There can also be black holes that are relatively light, but the weight is so incomprehensibly dense that an event horizon still forms in a small area. But especially with the black holes at the center of galaxies, we are indeed talking about incomprehensible heavyweights. Sagittarius, a star, SOS EOS, the black hole at the center of our Milky Way weighs, for example, 4.3 million solar masses. That's heavier than I am after I stuffed myself with 10 dumplings at Christmas dinner. That's a general overview of black holes, but how have researchers managed to look behind a black hole? Based on what I just told you, one would think that any radiation, including light, is swallowed up, and that as a result, the area behind a black hole should be in complete darkness for us. Albert Einstein, however, predicted visionary that there must be an effect that allows us to look behind black holes. In his general theory of relativity, which I have of course read completely and understood 100%, he described that there can be such a strong curvature of space-time that light from the back of a black hole is bent and becomes visible at the front. Ow. We remember that gravity not only attracts normal matter, like planets and gas clouds, even space and time. You can imagine space-time a bit like an invisible trampoline that we are all currently on. The heavier an object is, the more the trampoline is dented. The Earth, for example, and space-time to a certain extent. And in this dent, the moon orbits the Earth. That's roughly how you can imagine it. And with black holes, space-time can dent so much, I should patent the word, that it can wash light and optical information from the back to the front. Folks, if you eat as much roast and dumplings during the Christmas season as I do, think of your space-time dent getting deeper and deeper and deeper. We should all exercise more. However, Albert Einstein was not yet able to practically verify this effect. The technology for astronomical observation was simply not advanced enough, because even the existence of black holes itself was only absolute theory at that time. But as so often, Einstein was right in all respects. Because now researchers were able to prove the effect in reality, they captured X-rays that originated from the back of the central black hole of the galaxy Zwicky 1. Special knowledge for everyone. Fritz Zwicky was the most famous Swiss astronomer of all time, and this galaxy, which is 800 million light-years away from us, is named after him. This observation was achieved by the team led by astronomer Dan Wilkins from Stanford University with the help of the X-ray telescopes XMM Newton and NuSTAR. Using the data from these X-ray telescopes, they were able to determine that the captured X-rays originated from the side of the supermassive black hole in the galaxy Zwicky 1 that faces away from us, were reflected by the plasma ring of the black hole, and were thus deflected in such a way that they appeared delayed on the front side, that is, the side facing us. Now you might be wondering, what kind of radiation is that anyway? And what is a plasma ring? Shouldn't everything be swallowed up so that there is no radiation at all? Around black holes, a so-called accretion disk often forms, which is a huge ring of the material that is being drawn into the black hole. In this accretion disk, there are intense frictions and enormous amounts of energy are generated, leading to massive energy bursts known as jets. These processes around a black hole indeed generate a lot of radiation, which can then be observed, among other things, in the X-ray range. But how did the researchers at Stanford University know that they had captured the radiation from the backside of the black hole? It's not like it says backside on it or anything. An X-ray burst appeared based on its measured properties and timing, like a weaker, delayed echo of a previous energy burst. Additionally, the team states that the energies of the individual subbursts in these outbursts suggest that they must have been reflected from different parts of the accretion disk. Dan Wilkins says the analysis of the X-ray flares reveals brief bursts of photons, whose characteristics match an emission originating from the backside of the black hole. These are light particles that bounce off the far side of the disk and are bent and amplified by the strong gravitational field around the black hole. Humanity has thus managed to detect light from the backside of a black hole for the first time. And Albert Einstein was right once again. Peace, joy, space-time dent.
And if you still haven't had enough of the cosmos and the many scientific insights, feel free to click here on the right and you'll find even more exciting topics. Every click helps the channel to grow, otherwise I'll see you in the next video. Take care, folks.